Good morning, guys. Okay, as I have told you during the live class, today's video is for the next chapter, which is magnetic induction. So a little bit portion has been already covered during the live class, and we stopped till which one? Faraday's second law, right? So as per Faraday's second law, whenever coil is kept, coil means which is having a circular form or a rectangular form, just that it is in a what? Not ending, no terminals, it is a closed loop, right? Like that coil, if it is kept in a changing magnetic field, right, or changing magnetic flux is kept, then induced EMF or an induced current will be accepted or will be forming in that coil, right? Now what we are going to discuss is, I told you earlier, we just knew that the magnetic field is causing an induced current or EMF inside the coil. Nothing has been mentioned about the direction, right? That what would be the direction of that induced current has not been told. Now that direction is given by the law called Lenz's law, right? So this Lenz's law only gives you the explanation for why minus is written in this formula. E is equal to minus d phi by dt. Why this minus comes up is told during the, or is explained by Lenz's law. Clear? Now we know more or less, or the magnitude of EMF is equal to d phi by dt. Please register that in your mind. Now what Lenz's law states is that the direction of induced EMF or induced current inside a coil kept in a varying magnetic field is in such a way that it always opposes the cause producing it. So that means if B, right, is a magnetic field which is varying, this varying magnetic field is causing a change in flux. This change in flux is causing a change in rate of change of flux. Right. Now when rate of change of flux changes, an EMF is produced, right? Now this EMF is such a way that its direction is opposite to the cause producing it. What is the cause producing it? The change in magnetic field. So if the change in magnetic field is in such a way that is increasing, means this EMF or this current, say that is I dash, should be in such a way that this induced current will be also having its own magnetic field, right? Say induced current is having a magnetic field, say B dash. This B dash will be opposite to that of B. If it is increasing, this B dash, and it is in, suppose is in into direction, means B dash will be also in increasing but in opposite direction. Right. So Lenz's law stated that the direction of induced EMF or induced current is always such that it causes or it opposes the cause producing it. I hope you didn't understand anything of it. Let's take an example. Let's take an example 1. See, if you want to have an example like this, see, this is the magnetic field. You are the person, or suppose this is your friend, right? So this is your field which is changing, and he gave a gift to you, right? So this is the coil, you are the coil, right? And you ate this gift, let's say this chocolate, and you were happy, so your energy increased. What did you do? You in order to say, or just in place of saying thanks, you slapped this guy. That means just like the proverb that the person is biting the other person who had given him any no profit or advantage, right? Biting the person's hand who has been favoring you, right? So this is the best example you can say. So the person or the magnetic field or the induced EMF which was present in this is in such a way that it opposes a cause producing it. Right, I will tell you an example with elaborate way in physics way itself, not with this layman language. Let's say this is your coil, right, and you are keeping it in an external magnetic field such that this magnetic field is increasing gradually, just like this case. And when this magnetic field increases, that means number of field lines will be very close to each other. Number of field lines when they are close to each other, that means the flux lines or flux is increasing. That means d phi by dt has increased. That means EMF has been introduced or current has been introduced or induced. Now, as per Lenz's law, this induced EMF or induced current has the direction so that it opposes the magnetic field which has been producing it. Right. So here, let's say if B is into direction, that means this coil should have a direction of current such a way that the magnetic field due to this induced current should be in opposite direction. That is, say if I dash is the induced current flowing through this coil. Now this induced current's direction, how can I say? The direction. So this induced current will be having its own magnetic field, right? Say B dash. Now B dash is due to not this magnetic field. It is due to B is this one. Okay guys, don't confuse it. B is the magnetic field which you have applied. Say, and B dash is a magnetic field which is arising due to the induced current inside this coil, because every current carrying coil produces a magnetic field which you have learned in the previous chapter. So this magnetic field B is external and B dash is the magnetic field which is coming due to the current flowing through this coil. Right, say, so this B dash should be in which direction? If B is into, then B dash should be outwards as per Lenz's law. So B dash, if it has to be outwards, that means this is the magnetic field which you want. That means in which direction the current should flow? In this direction. So that means I dash current's direction is like this. Clear? Right. So that means in which direction it is flowing? The current is, I dash current is in anti-clockwise direction. Right? See, B caused I dash. B caused I dash. Now I dash flows in such a way that it causes a magnetic field, right? B dash. That B dash in outward direction. Now this I dash nature is what? This I dash current is opposing B. Clear? Opposing B means it is trying to reduce the effect of B. Clear? We'll do a little bit other examples, guys. Let's take a square loop. Now I'm going to take a magnetic field where magnetic field is outwards. That is towards your face. Right? I'm keeping a, say it is a rectangular coil here. Now again, what I'm going to do is I'm going to reduce the magnetic field. So whenever there is a variation in magnetic field, so flux is also reducing, d phi by dt is reducing. That means EMF is reducing, or let's say is induced. Whenever there is a rate of change of flux, EMF is induced. So EMF is induced, or I can say current has been, let's say that is I dash. Induced current is happening. This much clear? Now what will be the direction of induced EMF? Take your time, draw it by yourself. Then that means now you have to pause and draw the figure. Then listen to the video again, guys. Now what has happened, guys? I dash. So I have to find the direction of I dash. How can I confirm the direction of I dash? This I dash has to cause a magnetic field, say B dash. Okay guys, this is the same figure as I drawn. As you can see, the figure was distorted by some reasons. So I have redraw here. So extremely sorry for that. The same theory. So you wanted to draw what the direction of current is, right? So the current should be in such a way that it opposes the cause producing it. What was the cause, guys? This was the reduction in magnetic field. So the current should be flowing in this magnetic coils or the coil in such a way that it causes the magnetic field or the net magnetic field to increase, right? Decreasing was the cause, means it is opposing, means the magnetic field due to this current, that is induced current, should be increasing the magnetic field. So how can it increase the magnetic field? That means the magnetic field due to this coil or magnetic field due to this induced current should be also in outward direction, right? So how can the current or direction will be so that the magnetic field is in outward direction? That means the current should be in this direction, right? So the current is in this direction. This much clear? So that now see, this I dash is in this direction. So what is the magnetic field outward? Say that is B dash, right? Sorry, say B dash. It is in outward direction. B is also in outward direction, right? So net magnetic field, both of them say is in out direction, means they have adding, right? So the net magnetic field will be what? Increasing. So initial, what was the cause? Reduction in magnetic field. What was the net result? The current was induced. What was the induced current's problem? It caused the reduction of magnetic field to be stopped and it caused it to increase further. So that is the Lenz's law. Clear? Now let's take another example, guys. Same I am taking a square coil. There is a current not flowing here, but a current carrying infinite wire, right, is kept close to it, right? So this is a coil, this is a straight wire. So any straight wire, infinite wire, will be having its own magnetic field. I have taken it, guys. So if this is the direction of magnetic field, I hope you remember this direction. So in which fingers are going inside, right? It goes inside here and comes outward, right? In this side it is into, in this side it is outwards, right? Clear? So here only I'm going to draw. So this here is outwards, right? I hope you remember the formula, that is P is equal to mu 0 I by 2 pi r or 2 pi a. That was a formula for the magnetic field which is produced by a current carrying infinite wire. Now let's say I'm increasing the current, right? Now increasing the current means magnetic field increases. Magnetic field increases, my d phi by dt increases. That is, induced EMF is now increasing. This much clear? Now what should be the direction of the current in this coil? Pause the video and try to draw it by yourself, guys. That means the induced current which is flowing here should be in such a way that it opposes the nature of current which is producing it, right? Now this induced current which is I dash will be flowing this, right? This I dash should be opposing means what? It should reduce the current, right? It opposes the current producing it, right? Current is producing it. Current is increasing the magnetic field, right? So if this I dash is the induced current, its nature should be such that it opposes the increase in magnetic field. It opposes the increase in magnetic field in the sense it should produce a magnetic field B there such that it opposes the increase means it should reduce this magnetic field, right? How can it reduce? By minusing it. So that means if this magnetic field here is into, right, that means B dash should be outward direction. Right? How can B dash be outward direction? That means outward direction means how can I draw this current's direction like this, right? If this was the current direction, see, let's say, take your fingers by yourself, okay? If this had been the current's direction, so in which direction the current I have known, I have drawn this, right? So that means the current is in which direction? Clockwise direction. Current is in clockwise direction means, see, this is the clockwise direction of the fingers. So my thumb is into. So here, due to this current, the magnetic field is into. This dot is due to B, whereas this cross is due to B dash. So net section is reduction of the cos, which is B is reduced. Clear? Right, let's take another example, guys. Suppose, same, right, but I'm taking this and changing the scenario. The current carrying wire is like this such that the I current is constant. But what I'm going to do is the coil, which is the rectangular coil, I'm going to move it away. With the velocity V, say, just moving away. And the same scenario, right, say here the current carrying coil means here the magnetic field is into. So into direction like this. Okay, now it is moving in velocity V. Now what happens? See, V changes means magnetic field changes. It is cutting the magnetic field lines, right? So when magnetic field lines is cutting means there is a change. Or if you didn't understand, let's say like this. This coil is moving away, right? So when this much section that is very close to this current carrying coil will be having strong magnetic field, whereas this side, let's say this point is away from the current carrying wire, so there the magnetic field will be less, right? So that means this coil is moving from a stronger magnetic field to weaker magnetic field. This much clear? That means I can say the magnetic field is getting reduced. That means phi is getting reduced, same. So EMF is obviously introduced and current has been induced. Now what will be the direction of the current inside this coil? It has to oppose the cos producing means it has to oppose the reduction in magnetic field, right? That is, this reduction has been induced in the coil due to its moving away, right? Hence, to increase the magnetic field, the current, induced current, that is I dash, must flow in which direction? It should say, suppose this say, let's say it is in clockwise direction. I am telling you how. So if it had been this is clockwise direction. So this induced current clockwise direction means the magnetic field is in which direction? Into, right? Let's say this into, I am going to mark it like this. Right? With circle means it is due to the induced current, guys, and without circle is due to the wire. Right? This is also in into direction. This is also in into direction. This is B dash, this is B. What will the net magnetic field will be sum? That means it is increasing the magnetic field, right? So that means the cause was the reduction of magnetic field, but the end result is such a way that the induced current causes the increase in magnetic field, right? Now let us take another example. I'm taking examples so that you guys can understand the entire topic, guys. Now let's say then another coil I'm going to take, right? I'm going to bring a permanent magnet. Say this is north and this is south, right? So magnetic field lines will be like this. Now what will be the nature or how will be the direction of induced current inside this coil? Take your time, try to draw it by yourself, guys. I hope you have drawn the figures or the coil's current direction. If not, listen, guys. There is a short trick for it, but before that I want you guys to understand the section. Right, now just like the previous case, say this north pole is producing magnetic field lines like this. Now say, okay, I didn't mention, suppose it is moving towards the coil, right, velocity, right? So now again pause the video, guys, and now do the current coil's direction, current direction. Okay, after pausing, I think you have drawn the figure. If not, listen. See, now I'm assuming that this magnet is moving towards the coil. That means number of wheel lines increases towards the coil. So you want the coil to have a current direction. Induced current will be there. I'm not going to write this magnetic field is increasing, d phi by dt is increasing, because you know. Now magnetic field lines increased, right? So you want the current direction in this coil in such a way that it opposes. That means if this is moving towards here, you want the current direction such that it opposes. That means the magnetic field lines should be in which direction? In which direction, guys? It should be also, that means in, I hope you remember the south pole, north pole direction of a coil. If not, I'm going to write here, guys, just like small section. I hope you remember north pole, right? Like this, the current flows in this direction. That is in a current coil, current carrying coil, the current's direction is in anti-clockwise direction, then that facing section acts as the north pole. Similarly to a coil where the current is there flowing in clockwise direction, right? I drew earlier wrong, that's why I'm taking it again, guys. So if the direction is like this, right, your clockwise direction, so that means south pole. If it is an anti-clockwise direction, it is north pole. So just like that, I'm going to come back here. If not, if you have drawn it, well and good. So this coil should oppose the cause producing it. Opposing means what polarity should be there in this coil? There should be a north pole, right? So this should be acting as a north pole. So that means the current direction should be like this, right? That means anti-clockwise direction. Then only this acts as a north pole, it opposes, that means this magnet can move away, right? Now similarly, the same case, guys, if this is a coil, right, and you have a north-south magnet just like this, but it is moving away with a velocity v, say, right? So if it is moving away, so that means this moving away has caused the induced current inside this coil, right? So moving away has to be stopped and it has to be brought near. So what should this coil become? This coil should become which pole? South pole, right? South pole means the current has to flow in clockwise direction like this, right? Now this coil is acting as a south pole. That means now this magnet can be attracted, right? This is how the polarity is drawn. This much is clear. Now same can be drawn in the case of what? Top bottom, right? Say suppose this is my magnet, this is north and this is south. Say the coil has been placed in downward direction, right? So you want this, suppose this is moving downwards with a velocity v, which this magnet, you want this magnet to be what? Repelled, right? Repelled means this coil should be acting as south magnet or south polarity. That means the current's direction should be in this direction. Very easy. Similarly, if this is the magnet same, this is north, this is south, it is moving up, right, away from the coil. So you want the coil to be according to the Lenz's law. This movement away has caused the induced current. This induced current should bring this magnet towards it, right? So this should be acting as what? North pole, right? So the current's direction should be in this direction. This much is being cleared. Say our last 5 minutes we'll go through the entire thing again, guys. So I am taking it proportion wise so that it will be very easily understandable. Right. Now what will be the acceleration? Whether there will be any, suppose, see, this is just like dropping a magnet, right, towards a coil. Right. So what will be the acceleration? See, if this magnet is trying to move towards this coil, this is south and this is south, that means maximum repulsion is happening, right? So the acceleration due to gravity it is not achieved. The acceleration due of this magnet will be less than acceleration due to gravity, right? Because there is a repulsion, it is trying to fall downwards, but this magnet or this coil which is acting as a magnet is pushing it outwards. So acceleration will be less than g. Now here what is happening? It is trying to move away, but this coil which is acting as a north pole is trying to bring it downwards. So the acceleration is greater than acceleration due to gravity. This Q section is also very important in the case of NEET. Let's now brush up. This much is clear. Let's brush up to the entire section which we had taken, guys. Lenz's law. What is Lenz's law? Lenz's law states that whenever or the direction of the induced EMF is always such that it opposes the cause producing it. And this say, okay, I forgot to say, that is, it is proposing the cause producing it, right? So EMF direction is opposite to the flux or magnetic field, that is indicated by this negative sign. If flux is negative, then minus EMF becomes positive, like that. Clear? Okay, so let's move on. See, we took a coil. Right, this coil was kept in a magnetic field which was what? Into, and you are asked what is the direction of current. The current's direction should be in such a way that the magnetic field, I am not talking here about increasing, I am just telling the increasing fact comes later on. We have just kept it a magnetic field which is into. Now when this magnetic field is into, then the magnetic field due to the induced current inside the coil should be what? Outwards, because that magnetic field is into. Right? This much is clear. So that's why this current is anti-clockwise. If you don't understand anti-clockwise, this is magnetic field's direction. So B dash is in this direction, B is in this direction. So both of them are in opposing nature. Let's say if it is increase. Usually it is increase. I wanted to make you understand how to take the direction. That's why I talked about here. Now we are going to gradually decrease the magnetic field. Right? And I'm taking an example. Magnetic field here is outwards. That is towards your face. I have drawn it here again. So the magnetic field is what? Decreasing. The flux is decreasing. Obviously the EMF is induced now. Current has been induced. Now what will the direction of current be? The current should be having this direction such a way that the magnetic field due to that current is opposing the cause producing it. What is the cause here? That is the decrease in magnetic field. So opposing the decrease means it is, that is negative of negative is what? Positive. So decrease in magnetic field should be changed into increase in magnetic field. So how can it increase? If it is flowing or if that induced magnetic field is in the same direction as that of the magnetic field. Right. So here say this magnetic field B is in decreasing direction. So B dash, say this is in outward direction, right? So this is outward. Now this current, let's say I have drawn it, right? So the current's direction, I'm taking this much fingers. The thumb is also in outward direction. So B dash is outward, B is also outward. So B dash and B has to add up, right? So decrease in magnetic field is changed into increase in magnetic field. It is not allowing it to decrease in a sense. Clear? Now we have taken another example also. I believe we drew this one first, right? So suppose you are having a coil which is close to a current carrying wire. Current carrying wire will be having a field. This field is in outward direction. So what will be the direction of the current in the inside coil? It should oppose the cause producing it, right? The current is being increased. So this field which is outward direction is also increasing. So that means the induced magnetic field, right? The magnetic field due to the induced current should oppose it. So this magnetic field is in outwards. That means the magnetic field due to I dash should be inwards. So that's why cross, right? Cross means this should be the magnetic field. So which direction the current has to flow? In clockwise direction. Right? Now similarly we are drawing this one. Right? So here what we are doing, we are moving the coil away. Coil is moved away, right, and the magnetic field due to this current carrying wire is into, right, and this is moving away means obviously EMF is induced, varying magnetic field, right. Here the magnetic will be strong, it is weak here, so moving away from strong and moving towards weak. Now the magnetic field will be what? Decreasing. Magnetic field decreasing means the magnetic field due to the induced current should be causing it to increase. Causing it to increase means the magnetic field B dash should be also in which direction? It also should be in inward direction. So that means it should be in clockwise direction, which current's direction. Similarly, permanent magnet case also, right? If you are bringing a north pole towards a coil, then it is brought near. That means you are trying to oppose means it has to be pushed off. It has to be pushed off means the polarity of this coil should be north. That means the current should be in anti-clockwise direction. Similarly, if the magnet is moving away means you are, according to the Lenz's law, it has to be brought in or towards. That means the polarity should be south. That means the current should be in which direction? In clockwise direction. This much is clear, right? Acceleration, I don't think I have to tell you again. Okay guys, so please listen to the video again and again, try to understand it, and I believe it is very easy if you listen to the video twice or thrice. Okay guys, bye.